Okay, in the last lecture we have been discussing about the three body problem. So, one of the major problem of this three body motion. So, what we saw that there this problem is absolutely not solvable. Even the two body problem, we saw that in the absolute sense the two body problem cannot be solved. Only in some relative sense we were able to get some meaningful solution to that. But in the three body problem, obviously we were far away from any tangible solution. But if we do some assumption, if we make certain assumptions, then under that assumption it is possible that the solution to three body problem can be obtained. Say in the case of the earth and the moon system, we can have a satellite which can be treated as a third body. So, satellite can be treated as a mass of as a third body of negligible mass. So, under that assumption if we start working, so it is definitely we are going to get certain solution which are very intuitive, and it gives us a feeling how the third body is moving with respect to these two primary bodies. So, let us start with the very basic assumptions which we make for the motion of the three body in this case. So, this we call as the circularly restricted three body problem. So, the first assumption is the primary and secondary bodies move in circular orbit. Circular orbits about their center of mass. So, the benefit of this assumption that the orbit is circular, you can directly see if the orbit is not circular. So, obviously, here the omega of the primary body it will be changing with primary bodies will be changing with the time. So, in the circular orbit what we have that the angular motion, the angular velocity of the satellite, okay, if this is the radius r, okay, v is the velocity. So, in a circular orbit this v remains a constant and therefore, omega is also a constant. Okay. But in elliptical orbit we get extra complicacy in the sense that here omega becomes a function of r again. So, beside this assumption, the second assumption we make the third body is very small as compared to the two larger bodies. So, here the primary body this is assumed to be quite large as compared to the secondary body, and the third body it will be assumed to be quite a small as compared to this primary and the secondary body, and so that its mass can be neglected. So, mass can be neglected. And the third assumption, which is again which gives further restriction can be made, or sometimes it is made, is that this is additional constraint. I will put this as additional constraint. Only under these two constraints we can work, but sometimes this may be available. So, additional constraint. Okay. So, under this is the third body constrained to move in the orbital plane of primary and secondary body. So, let us consider we have two masses m1 and this is m2. The center of mass of these two masses, it lies at say B, we write as the barycenter. Okay. So, both of them will be moving about the center of mass in a circular orbit. So, this will describe a circular orbit of radius from here to here, this will continuously move. Similarly, m2 will also move, but they will always remain along the same line. Okay. It will never happen that this line, the angle between from here to here, let us put here as A and this as C. So, outside A and this is C. Okay. This is mass m1. Okay. So, both the masses they must lie along the same line. You can see yourself that if they are not lying along the same line, and barycenter cannot be somewhere else, they have to always over this same line, and therefore, their period will also be the same. Okay. Now, let us assume that we take the a reference frame which is fixed to the barycenter, but not rotating along with the satellites. Okay. So, this barycenter, the reference frame fixed at the barycenter, this will call as the inertial reference frame, because the barycenter is, we know that if the two particles or n number of particles, they are free from the external forces. If they are free from the external forces, then their center of mass moves with a constant velocity. So, therefore, we can fix an inertial reference frame at the barycenter. So, in this case, we take the barycenter, let us say as x b is the unit vector along this direction, and then we have y b is the unit vector perpendicular to the x b, and x b and y b they are lying in the orbital plane of m1 and m2. Okay. Therefore, z b it will be coming out of this plane. Okay. So, z b will be perpendicular to the plane of m1 and m2, the orbit of the m1 and m2. Okay. Similarly, we here this is the center of mass. Okay. Similarly, we fix another reference frame which will be rotating at the same rate as this line joining the mass m1 and m2 is rotating, means that will be the period of the reference frame which is fixed at this point at the barycenter, but it is rotating along with the masses, and its period will be same as the period of the period of these two masses. Therefore, we take the direction of this, let us say this is the x s, the x s cap. So, this is the x axis of the here the subscript s stands for the synodic, this is called synodic reference frame. Okay. And this is our x body, x axis of the x axis of synodic reference frame, and this is the x axis of inertial reference frame. Okay. So, the y axis of the synodic reference frame, it will be pointing downward. Okay. So, here x s and this becomes y s cap. So, this is the unit vector in the y direction for the synodic reference frame. So, the whole reference frame will be rotating along with the these two primary and the secondary bodies. Okay. And then z x, which is the z axis of the synodic reference frame, it is again coming out of the plane of the paper, or the which is here in this case we are assuming to be the plane of these two masses, it is a plane of the orbit of these two masses. And let us assume that the m is the mass of the satellite, which is quite negligible as compared to the mass m 1 and m 2, and we are assuming here also m 1 is greater than m 2. R is the radius vector of the satellite in the inertial reference frame. Okay. Similarly, you can have the this we can write as R 1. Okay. And this is as R 2. So, R 1 and R 2 are the radius vector of the satellite mass m. This is the third body from the mass m 1 and from the mass m 2. Okay. So, the equation of motion of the mass the body 3. So, the third body motion can be written as minus k times or minus g times m 1 m divided by r 1 whole cube So, our assumption that this mass third body mass is quite small as compared to these two primary masses. So, that simplifies the situation that these two the motion of these two masses can be ascertained quite easily, as we have done earlier for the two body case, and where the mass of the third body, because it is very small. So, it is not at all affecting the motion of these two primary and the secondary bodies. Otherwise, if this mass becomes quite large, then equally it will affect the motion of the primary and the secondary mass, and therefore, it won't be possible to solve this motion at all. So, under this assumption we get d square r dt square Now, here d square r by dt square, you can write this as r double dot. This is nothing but the inertial acceleration of the third body in barycentric inertial reference frame. So, r double dot, which is the inertial acceleration of the third body. Okay. So, this can be written in terms of This can be written in terms of the motion of the, see here in this case this is our third body. So, this acceleration we have got in terms of in the inertial reference frame, but we want to describe the motion of the third body with respect to the moving reference frame. So, what does it signify? It signifies that our two masses are moving in this plane, and with respect to these two masses, means the line joining these two, then how the motion of the third body can be described. One is, so this becomes again the relative motion. This is not the motion in absolute sense. Okay. So, this is a relative motion that we are trying to ascertain. So, it is a very important that if we have the third body moving with respect to these two primary bodies. So, what will be its location at any other time or is any other time in the future with respect to these two primary and the secondary bodies. So, it will give us insight. Say I want to locate certain satellite with respect to two bodies, then how the satellite motion will get affected with respect to these two bodies. So, that must be known beforehand. So, that can be done if we assume that if we try to resolve the motion, the inertial motion with if we try to get from the inertial motion the motion with respect to the moving reference frame, which is the synodic reference frame here. So, we try to convert the inertial motion in synodic reference frame. So, for doing that we know a very simple kinematic relationship, which we have done earlier in our earlier lectures. So, r double dot, which is nothing but the inertial acceleration, this can be written as, say, r double dot s plus. So, what exactly r double dot s is, I will come to that. So, here this part, this is the acceleration of the origin of the synodic reference frame with respect to the inertial reference frame. So, because the synodic reference frame is fixed at the barycenter, okay. So, it is not having any translational motion, and therefore, this quantity becomes equal to 0. Besides, omega s dot, this quantity equal to 0. Why this is so? Because we are assuming that the two primary and the secondary bodies, these two bodies, they are moving in a circular orbit, and therefore, the omega s is the rate at which these two are moving about their center of mass, and therefore, if we fix a reference frame at this point at the barycenter and let it move at the same rate, means the omega s, the reference frame will also move at the same rate. So, therefore, the benefit of the circular orbit is that here we are not getting any change in the angular rate of the synodic reference frame, and therefore, omega s dot can be set to 0. Okay. So, these two greatly simplifies our situation. Now, r s double dot, this is the acceleration of the third body in the synodic reference frame. And a small r s, this is the radius vector of the third body, which here in this case is a satellite. In synodic reference frame. So, we have omega s dot equal to 0 and rho s double dot, this quantity also equal to 0. Now, let us write so, here E1, E2 and E3 they are the unit vector in the along the 3 axes of the synodic reference frame. So, here we have actually used the notation S in this place. This is the unit vector along the x direction, and similarly this is the unit vector along the y direction. So, this thing actually this becomes E2 and this becomes nothing but E1 cap, and E3 cap will be coming out of this. So, this is just for the ease of notation, writing this is much easier. So, we can follow this. So, R s is equal to x times this is x times E1 cap plus y times E2 cap and z times E2 cap. This is a simple relationship. Okay. Similarly, omega s, the angular velocity of the synodic reference frame, it can be written as omega s times E3 cap. So, where omega 3 is the magnitude of the omega s vector and E3 is the unit vector in the along the z axis of the synodic reference frame. So, omega 3 is nothing but, or omega s we can write as this as omega s. Along the 3 axes of synodic reference frame. So, now we can evaluate the r double dot. So, this is the inertial acceleration. So, by inserting all these quantities here, so this omega s dot this becomes equal to 0. Okay. So, one by one we will be able to ascertain all of them, and therefore, we can express the inertial acceleration in terms of the components of the quantities which are given here. So, taking first omega s cross okay, one by one we work it out. So, we have E1, E2 and E3. Okay. So, E3 cross E1, E3 cross E1 this is nothing but E2. So, this become omega s omega is we have already taken out. So, this is x times E 2. Then we have E 3 cross E 2. So, E 3 cross E 2, this is minus E 1. So, this is y times E 1, and E 3 cross E 3, this becomes 0. Okay. Now, again working out this. So, E 3 cross E 2, E 3 cross E 2, this is minus E 1. So, x times E 1 cap, and E 3 cross E 1 is nothing but E 2. So, this is minus y times E 2 cap. This is our equation number 2. Okay. Also, we can estimate here itself omega cross V s. So, V s is the velocity of the satellite or the velocity of the third body with respect to the synodic reference frame. So, this become omega s E 3 cap cross So, E 3 cross E 1, this is E 2. So, x dot E 2 cap, and E 3 cross E 2 is minus. So, y dot E 1 cap, and E 3 cross E 3 is 0. Therefore, r double dot, this can be written as, so r s double dot. Now, the quantity we have shown here, r s double dot, this is the acceleration of the third body in the synodic reference frame. So, this will be nothing but x double dot E 1 plus y double dot E 2 plus z double dot E 3 cap, okay. And rest put other things. So, omega cross r s, this quantity we have just now determined. So, this quantity is minus omega s square x E 1 cap plus y E 2 cap, and then the third quantity which is remaining is 2 times omega cross V s. So, this become 2 times omega s times So, this is the inertial acceleration which are expressed in terms of the acceleration along the body the synodic reference frame components. These are the acceleration with respect to the synodic reference frame of the third body, and these are arising because of the rotation of the synodic reference frame itself. So, we can recognize these accelerations. So, this acceleration is nothing but the Coriolis term, and while this term you can visualize as the what you call as the centripetal acceleration. So, it is very easy to work it out and look into this. So, whenever some particle or some body is moving with respect to a rotating reference frame, so it feels some the what is called the Coriolis force. So, this is expressed here, this is the Coriolis term. This is the centripetal term. Coriolis So, also r double dot, this we can write as we have all earlier written as minus g times m 1 by r 1 whole cube Okay. Now, if we look into the original figure, this figure. So, R 1 is a in this equation R 1 is basically this is with respect to the inertial reference frame, means these are taken in barycentric reference frame. But if we look into this quantity and our reference frame, which is the synodic reference frame, this is rotating at omega. But what happens, either we take the inertial reference frame or the synodic reference frame, these are the invariant quantities, they do not differ. Okay. Only the components along their body axis will change, but as a whole this quantity remains invariant. So, therefore, we can express the R 1 and this R 1 and R 2 in the synodic reference frame itself, and therefore, we can compute the corresponding sum. So, what exactly we are doing? So, we know the acceleration here in the synodic reference frame, and the left hand side is the inertial reference frame, acceleration in the inertial reference frame. So, inertial reference frame components can be broken along the synodic reference frame, and that makes us easier to put this all these expression in a compact form. Okay. So, following this, we can put a subscript here to indicate these are in the synodic reference frame, because these are the invariant quantities. So, we have R 1 s, which is nothing but the r vector minus the mass of the we write it as R 1 b, which is the radius vector of the this quantity we can write as R 1 b. This is the vector from here to here. So, to the mass 1, this is the vector R 1 b. So, R 1 becomes R minus R 1 b. Similarly, here we can write this as R 2 b. Okay. So, R 2 that can be written as, so we can write here as R 1 equal to R minus R 1 b, and R 2 is equal to R minus R 2 b. Now, moreover, if the same notation will also follow in the quantity R 1 and R 2, they are invariant. So, these are equivalent to R 1 s and R 2 to R 2 s. So, we can replace in terms of this here in these quantities. So, once we replace it, so this expression will become further simplified. So, R 1 base R 1 is, then we can write as x E 1, means then we are expressing in terms of the synodic reference frame. So, R minus, where R is the radius vector of the third body with respect to the synodic reference frame. So, this becomes R minus R 1 b in the synodic reference frame. Okay. So, this we can then express as x times E 1 cap plus y times E 2 cap z times E 3 cap minus R b 1 s, and because this is in the synodic reference frame, this is directed along the x axis. So, here we will have this as E 1 cap, and this is okay. You can see here this is directed along the synodic x body x. So, therefore, whatever the magnitude of this vector is this, and this is multiplied by the unit vector. Okay. So, this again we can bring together and write them as E 1 plus y E 2 plus z E 3. Similarly, we can write for the R 2 s also. So, R 2 s, this can be written as R minus R 2 B s, okay, which is x E 1 plus y E 2 plus z E 3 and minus R B 2 s, and this is directed along the okay, R 2 B. R 2 B is here just directed opposite to the E 1 direction, it is here, and therefore, we can write this as, and E 1 is positive in this direction. Okay. So, minus E 1 cap. So, this becomes x plus R 2 B s E 1 cap plus y E 2 plus z E 3 cap. Okay. So, once we have written in this fashion, then we can assemble all the things together. Look into this equation R double dot, here the E 1 term can be brought together, E 2 terms can be brought together, okay, and E 3 will be left alone, and we can simplify this equation. So, R double dot, now R double dot, this can be written as x double dot minus x times or omega s square x minus 2 omega x times y dot, okay. This times E 1 cap plus y double dot minus omega s square y plus 2 omega x omega s times x dot. This is E 2 cap, and lastly the z 3, the z component, it can be brought here. Okay. So, once we have expressed this, so this will be equal to nothing but g times m 1 r 1 s whole cube, and then r 1 s vector we have to bring in here. So, that is x minus r b 1 s z e 3 cap minus g m 2 divided by r 2 s cube x plus r b 2 s plus r b 2 s times E 1 plus y E 2 cap plus Z E3 cap. Okay. Now, you can see that on the left hand side all the terms are grouped together with E1, E2 cap and E3 cap. Similarly, on the right hand side we can bring the terms together with the E1 cap, E2 cap and E3 cap and compare them. So, we get 3 second order differential equation. So, these 3 second order differential equation, they describe the relative motion of the third body with respect to these two primary and the secondary bodies. Okay. So, collecting the similar terms together, we can write x double dot minus 2 omega s y dot, this will be equal to minus g m 1 r 1 s whole cube b 1 s minus g m 2 by r 2 s cube plus r b 2 s. Okay. Similarly, the other two equations can be written. So, the other two equations, then for the y motion, y double dot minus omega s square x y plus 2 omega s x dot, this will be equal to minus g m 1 r 1 s whole cube y minus g m 2 r 2 s whole cube and lastly the z double dot, this can be written as minus g m 1 by r 1 s whole cube z minus g m 2 r 2 s whole cube times z. Okay. For simplification, we can assume g m 1 is equal to, let us say, mu 1 and g m 2 is equal to mu 2. Now, these are the 3 differential equations which describe the these 3 differential equations describe the relative motion of third body with respect to the two primary and secondary bodies. With respect to the primary and secondary bodies. Okay. Now, to solve these equations, so let us term this equation as A, this as B and this as C. To solve these equations, okay, but we do it in implicit way. But we do it in implicit way and this we achieve by multiplying the equations a, b and c. These are the equations a, b and c, and this we multiply by 2 x dot, 2 y dot and 2 z dot respectively and add them up. So, multiplying equations a by 2 x dot, b by 2 y dot and equation c by 2 z dot and adding them up. So, you can see that the terms that we get, this will be 2 x dot times x double dot, which is coming from this equation. Similarly, from the equation b we will get the term 2 y dot times 2 y double dot, and from the equation c we get 2 z dot times 2 z double dot. Now, next we take these two terms omega x, omega s square x and omega s square y, and here we do not have any other term. So, only one term is present in the equation number c. So, next we get 2 times omega s square and x dot times x plus y dot times y, and thereafter we have these two terms, and these two terms are of opposite sign, and this we are multiplying by x dot and this by y dot. So, they will cancel out each other, but still I write here in this place. So, we will have 2 into 2, this is 4, and this is 4 times omega s times x dot y dot and plus 4 times omega s times x dot y dot. So, these two terms will cancel out. On the right hand side we will have minus 2 x dot times rest other terms. From here we have to multiply by x dot, 2 x dot, 2 y dot and 2 z dot, and copy it here in this place. So, g m 1 we are writing as mu 1. Okay. So, 2 x dot mu 1 by r 1 s cube times x minus r b 1 s Okay. Next, this term we have to pick up. So, this equation is bit long, but we have to write it here. So, this is g m. So, g m 2 we replace as mu m 2. So, this is mu m 2 divided by r 2 s whole cube and x plus r b 2 s x plus r b 2 s, this term, the term which is present here, this is appearing, and we close the bracket here. So, we will have to take to the next page plus other terms on next page. So, left hand side we cancel out these two terms here. So, the other remaining terms are then this term is to be multiplied by 2 y dot. So, minus 2 y dot times mu 1 g m 1 we are writing as mu 1 by r 1 s cube times y plus this term becomes mu 2 by r 2 s whole cube, and this is also y, minus sign has gone outside here and here in this place, and then the last term is remaining here, which is again minus sign, we can take it outside, and this is 2 z dot and multiplied by this is mu 1 and this is mu 2. So, accordingly we write here mu 1 by r 1 s whole cube okay, and then multiplied by z plus mu 2 by r 2 s whole cube multiplied by z. Okay, so, after completing this, then the whole equation can be written as 2 times the LHS can be written as 2 times x dot times x double dot plus 2 times y dot times y double dot plus 2 times z dot times z double dot, okay, equal to plus the other terms we have minus 2 times omega s square times x dot x plus y dot y. This the we are writing the LHS equal to this. So, this becomes the first term becomes d by dt x dot square plus y dot square plus z dot square. Okay. If you differentiate, you get this quantity, and this term similarly we can write here 2 omega s square times x square plus y square, and this is d by dt. So, d by dt here we write. So, this is your LHS. So, this gets reduced to d by dt x dot square y dot square plus z dot square minus, okay, the factor 2 which is appearing here, this factor will not be there, because once we differentiate this quantity here. So, 2 will be appearing. So, 2 is that 2 gets accounted here. So, in another way, if we are writing it in this format, this 2 gets absorbed inside here. Similarly, this 2 has got absorbed here in this side. So, this we get omega s square and plus x square plus y square. So, finally, our equation gets reduced to the format d by dt x dot square plus y dot square plus z dot square minus omega s square times x square plus y square. This is equal to the all other terms. Now, we have to mention in this place. So, this is equal to minus 2 x dot x minus r b 1 s plus mu 2 times r 2 s whole cube x plus r b 2 s bracket close plus these two terms here. So, this is starting with minus sign. So, we put here minus sign to y dot minus 2 z dot times mu 1 by r 1 s whole cube times z plus mu 2 by r 2 s whole cube times z. So, and where we have written g m 1 is equal to mu 1 and g m 2 is equal to mu 2. So, we have got equation in this format, but still it is not complete. Okay, we need to integrate it. So, we will do that integration in the next lecture. Time is getting over. So, thank you very much. We continue in the next lecture with the remaining portion.